a pleasure to have it's a pleasure to have Simon Caron Huot here at our workshop, and he's going to talk about actually I forgot your title. It was something about causality and effective theory. So
Yes.
Thank you. Please go ahead.
Yeah, I would like to thank the organizer, hello everyone, and like to thank for inviting me to this conference and to present. I wasn't able to attend as many talks during the week because of a very constraining week. So please excuse me if I say things that contradict earlier talks or maybe are made obsolete by earlier talks. Well, contradiction should be unlikely, but yeah, please, please let me know. Also, please interrupt anytime during this talk. I think I try to have a relatively pedagogical first half. So okay, the grand goal of what we're trying to do is try to find causality is one important constraint we have on S matrices. Does it sound okay? I heard some feedback. I don't know where it was coming from. Yeah, so the general question is, what is a space of consistent S matrices? And this question, we understand now, is very important, especially since what's important are the boundaries of this space. And we learned, for example, in the case of the 3D-izing CFT, that theories that are at the boundary, you can actually solve them. Theories that are in the middle are kind of less, they're allowed, that's nice, but it's particularly exciting to map out the boundaries of the space of allowed theories. And one big question, $1 million question you can ask is QCD at the boundary? And if you can identify in the space of S matrices assumptions such that QCD would be like the unique theory which extremize certain quantity, then you could actually start computing physical observables. And so that's kind of the grand vision. And obviously this is too hard for today. So I'm not going to say anything of content about this program. People have tried for decades. Today we're going to look at setups where we have two scales, two separated scales that's going to be a very useful simplification. And that basically means that we're going to be talking about effective field theories that account for the effect of UV physics above some energy scale, which we call capital M, on the infrared, and we'll be interested in what can be observed in the infrared as a function of the scale M, and trying to be as agnostic as possible about what exactly happens in the UV. That's our general goal. So I'm going to spend some time discussing what is a 2-to-2 scattering, what does it look like in effective field theory. Then I will tell you exactly what axioms we use and the tools we use to connect the UV and the IR. And then I'll tell you some bounds, and there'll be two qualitatively different bounds. I was asked to speak mostly about the non-gravitational bounds, which came from, which would essentially be discussing a paper from last fall. But I will say a few words about the case where we have gravity turned on, because I'm sure many people here care about gravity. Should all do so. That's the general goal. So again, yeah, feel free to interrupt anytime. Yeah, and it's been this topic has a long history that I will not do full justice to everyone who worked on it. So okay, so the general idea of an effective field theory is you have some heavy physics, you have some light modes, and you want to parameterize the effect of heavy or short distance physics, which may be known or unknown on the long distance. And generally, you can expand the effect in powers of inverse power of the heavy scale. And this has a long tradition in physics. We apply this, in undergrad, we already applied this to fluids. That's why air and water are described by a very similar hydrodynamic equation, even though the molecules are completely different. We apply this to pions and QCD, standard model, assuming that something beyond it, but we don't know where it is yet. And actually, this framework is ideally suited for gravity, because below some the main scale at which we don't know things is the Planck length, which is very small. So, well, there are also things we don't know at longer lengths, but yeah, effective theory is very useful to characterize the effect of Planck scale or string scale physics on longer distances. So the basic point that has been appreciated for a long time is that causality restricts what you can write down in effective field theory. We're going to get more precise in a second, but a famous example, just to get started, is there was a famous example of if you write some higher derivative, like 4 derivative interaction for a scalar, okay, you expect this coefficient to be suppressed, but if you're just an effective field theorist, you just list everything you can write down, you might consider any sign of this thing. However, it turns out that if you really study this theory, it turns out that if the sign is wrong, you can turn on some phi backgrounds where perturbations will propagate superluminally, and you can even build like closed time-like curves. So there's something pathological with the wrong sign. And this constraint, it was observed, is actually equivalent to what you get from dispersion relations, where the idea is you write this interaction at low energies as an integral over unknown physics at high energies, but in such a way that all the unknowns have positive sign. So that gives you a sign constraint. So there are these kind of 2 viewpoints, and it's going to be physically clear that these sort of dispersion relation constraints are related to causality. But this approach of writing some rules is going to be much easier to systematize than trying to cook up time machines. So that's what we're going to pursue today. And so it's been pursued by many people, many more than I listed here. But the essential things, if you've heard about these causality constraints in the past, maybe I can say the essential new things today is that, well, we'll go away from forward limits, and we'll learn that there's actually a lot of information there. And also, it's going to pay off to exploit the full crossing symmetry, which had not really been done before, like a year ago or something. So that these are the 2 new ingredients. So there's actually some new things that I would talk about. Oh, there's a question. Thank you. Go ahead.
Is everything that you can learn from thinking about time machines, can it be understood from these dispersion relation arguments?
It's unknown.
It's unknown.
Yeah, it's unknown. Right now, I mean, for some time, for example, Madasena et al., they are the Edelstein, Zhiboidov, there are arguments that for some time were possible to do with time machines and not with dispersion relations. I believe that the state of the art now is basically we can do more, I think, with dispersion relations. But you know, I think it's nice to push these 2 viewpoints together. It's not entirely clear how they map to each other.
What about the other way? Could there be, I mean, is there an example of something you can get with the dispersion relation that you can't get with a time machine?
Yeah, I would give some examples. Yeah, I think so. Yeah. Well, that doesn't mean you can't, but you probably have to cook up a more clever setup than previously done. Yeah. Yeah, I'm going to vastly generalize this bound if that's what you ask. Yeah. So let's recap a bit. So we're going to be talking about effective theories of 2-2 scattering. Let's recap. So the way probably most of us learn about effective theories in grad school is that there's basically a recipe by that's attributed to Landau, is that, well, you identify the like degrees of freedom, the symmetries that satisfy, which sounds really easy, but it's actually the hardest step in practice. But once you have that, then you just write down the motional Lagrangian that these things satisfy, and you organize this Lagrangian in terms of power counting rules. And usually we focus on the relevant or marginal things, which are the things you mostly see. Today we're going to focus on the corrections to that. So higher derivative corrections. So as an example, if you have a really scalar field phi, we're going to assume relativity. So you can write down like a kinetic term, 2 derivative, and you can write down like in principle higher derivative correction. You have a cubic term. You can also write a bunch of derivative corrections and same ... Okay, so today is about the second line, all these derivative corrections. There's an important thing that one has to realize from the get-go in any effective theory is that this field phi is not a well-defined physical observable, and you can redefine it, and it's just like you can think of it as an integration variable in the path integral. You can do it. It's not so the action is really defined modulo field redefinition, and you can use that to get rid of many terms. So for example, order by order, you can, by doing changing phi by derivative, order by order, you can get rid of all these terms in the kinetic term. You can push them out, and there may be something you cannot push out, but that would be some heavy particle that's beyond your effective theory. But within the effective theory, there's no observable effect from these terms. So you can push all the effects. If you do that, you will push some effects here. But again, here, these cubic terms, you can also remove. And actually, all the effects are, for the scalar theory, you can push into the 4 point. Okay? So, and the general way to think about it is that the observable effects, well, the terms in Lagrangian that have observable effects are in one-to-one correspondence with polynomial S matrices. Okay? So there's a cubic one you can write, which is this phi cube for G, and then there's a usual phi 4. Then if you start listing the one with 4 derivatives, with 4 fields, who contribute to the 4-point amplitude at 3 level, the Lagrangian is defined modulo total derivative, and this field redefinition basically mods out equation of motion. So listing these, if you try to list derivative, it's a painful job, but the easy way to do this is just to list on-shell amplitude. And if you have a 2-derivative thing, the only thing it can become on-shell is S plus this S, or some power of Mandelstam. And here, if it's an identical scalar, you have to have something both symmetric. So it's going to be S plus T plus U, which is just a constant, equal to the external masses, which are going to set to 0 in the stock because I'm interested in a light and a heavy scale. So the effect of a heavy scale on a light scale, it's not going to matter what the light mass is. Okay, so there's actually no dimension 6 operator you can write down that's observable in EFT for this scalar. But at the next order, you can write a single interaction that goes like S squared plus T squared plus U squared. At the 6th derivative order, there's a single guy, STU. So your more general Lagrangian that captures all the observable interaction looks like this. Okay, G2. So G2 is going to be the leading guy. That's the d phi square 4 derivative. G3 is 6 derivative. So I use a subscript that are like power of Mandelstam variables. G4 is S4 and so on. Yeah. And this Lagrangian is in one-to-one correspondence with 3-level S matrix. And then, of course, you're supposed to add loop corrections. I mentioned briefly what you do, but the enumeration game is done by listing polynomial S matrices at 3 level. Okay. And all of these, the advantage of focusing on the amplitude as opposed to Lagrangian is that this is actually a physical observable. So you can impose consistency conditions on it. Okay, these observables are going to be constrained. And so everything you write here is observable. So our goal is going to get bounds or inequalities. We're trying to make statements about these effects. That's our goal today. So let me describe a bit what happens in the general case. So with spin. So each contact term has 2 properties. There's of course a scaling dimension. That's what you always focus on, which gives you the power counting. There's another property that will be very important today, is a spin of an interaction. I'll spend some time on it because it's less familiar probably to most of us. So it's basically the maximum angular momentum. If you do its partial wave decomposition, it's its maximum angular momentum in any channel. So let me give you an example. Suppose you have a non-integral scalars and you have this interaction, S squared TU. So if I look at a fixed S partial wave decomposition, then T is basically the scattering angle. So I can, and U also, so I can eliminate U in terms of T. So this amplitude is equal to this. And at fixed S, this is a quadratic polynomial in T. That means that it's a combination of Legendre polynomials of spin 2 or less. Okay, so we say that's the spin 2 interaction. This interaction has spin 2 in the S channel. In the T channel, now you have S squared. You can also write U in terms of S. It's actually cubic. So this is a spin 3 interaction in the T channel, and same in the U channel. So we say that this is a spin 3 interaction. So that means that there's some Regge limit in which it grows like energy cube. Okay. So yeah, I haven't defined a Regge limit yet, but it's basically forward scattering. So you fix one Mandelstam and take the other to infinity. So yeah. So the spin of interaction is very significant for this causality constraints, because our main tool are dispersion relations. So we use causality gives us analytic properties that we use to connect the UV and the IR. So the argument we're going to do in a second are going to involve contour integrals like this, where part of the contour is computable in the EFT at low energies, and part of the contour involve high energies that are unknown. And analyticity relate those two things. So we get integrals of this type, and the integrals that are kind of interesting are moments like this. So if you put inverse powers of S, we'll see in a second how many powers you need to make the integrals convergent. If you make the more inverse powers of S you get, the more suppression, because the integral starts at M, so you get 1 over M M2K, right? You get inverse powers of the cutoff suppression, the more subtraction you put. And if you plug in this contact interaction onto these moments, you find that the contact term of spin J is killed by our higher subtracted sum rule, right? I'm just saying that if you have an amplitude that goes like S squared in the Regge limit, and if you do something like contour integral of ds over S4, it's just going to give 0. Okay? So if you put too many subtractions, you kill the contact terms. So the spin of an interaction tells you which dispersion relations probe it. So spin J interaction is probed by J subtracted dispersion sum rules or less. That's a key idea. This relation between spin and number of subtraction is actually the right way to think about dispersion relation for when you have external spin. Like when you scatter gravitons, the scattering amplitude involving gravitons, I believe we've all probably seen spinorilicity variables in this week. You can write as a bunch of polynomial in spinners time a function of Mandelstam variables. But because these polynomials in spinner here, this thing here goes like S to the 4, right? Because this thing grow in the Regge limit, this F here has a different behavior than you would normally think. So, but if you think about the contact interactions for spinning case still have to be polynomials in spinners. So the first contact interaction you can write down is F equal to constant, and that's like actually like a Riemann to the 4 term in your Lagrangian. Okay, that would give you a constant polynomial in Mandelstam. That would give you that amplitude. But because if you try to do the partial wave expansion of this thing, you learn that this is a spin 4 interaction because of all these contractions. So something that's a constant, it looks like a constant, is actually like a spin 4 interaction. And now we can ask, well, what sum rules are you allowed to write? And the answer is that, for example, well, something like, maybe I should give another example. If you write something like ds over s, that's an unsubtracted sum rule. Because the quotient of f goes like s to the 4, that will be a spin 4 sum rule. Okay, so even though it doesn't look like it's a subtracted sum rule, it has all the properties of a 4 subtracted sum rule. So in other words, when you have spin, you effectively get subtractions for free. It's a phenomenon known as superconvergence, and it makes this causality constraints much more powerful when you're scattering spinning particles, just because you have to pull out these factors in front, which grow in the Regge limit. Okay? So that's a kinematic effect that is well known to those to whom it is well known, also known, called superconvergence dimension. And just to maybe illustrate the effect, I've created this table here. It's not published, but it's essentially based on a similar table from this paper last year. You can list all the standard model interactions and classify all the interactions in terms of their spin. So let me just walk you through this table. So just for pedagogical purpose, so the first one here is that's like Higgs the fourth. That's a Higgs self interaction that we know is there. For scalar, this is the Yukawas. This thing here, this dimension 5 thing, is basically the neutrino mass term, famous Weinberg term. I've crossed things that you can't actually write down, like you cannot write a cubic scalar thing in the standard model because of the gauge symmetries. So these things have maximum spin 0 and 1, sorry, 0 and half. And we're going to see later that the things we can probe with dispersion relation need to have spin higher than 1. So these things you can't probe by any dispersion relation. Okay. On the other hand, things with spin 1, there's a whole bunch of these. So this is dimension 6 operators like F cube. This thing here is a dimension 6 operator that's basically, X dagger X, H dagger DH square. These are some, the other ones I'm going to give some name. There's some like anomalous magnetic moment of stuff. There's a whole bunch of dimension 6 operators in the standard model. And they basically all have maximum spin 1, which means that dispersion relations marginally converge on those terms. We don't really know if rigorously if they converge. But all else, if you keep going on this table, everything else you can write down is probed by dispersion relation. So here, this has spin 3/2. So this is an interaction involving fermions and scalars, derivatives. So everything else is fixed. And maybe one general comment I want to make also before I specialize to scalars is that there's something really cool that happens in gravity. This amazing phenomenon, which is related to the fact that graviton has spin 2, which is all the contact terms you can write down involving gravitons, like R cube and even like R, F square, all these terms. There's always a channel where they grow with spin 2 or higher. So everything you can write down that relates to graviton is probed by a dispersion relation. And furthermore, there's just 3 things that have spin 2. Everything else has spin 4 and higher. That was observed in this paper. That essentially implies that something with spin 4 and higher is going to be automatically suppressed. It is not even a chance. All these coefficients here, we know that they have small coefficients. The only thing you potentially have to worry about are these things. But there are cubic interactions that, in fact, well, except for one, but yeah, cubic interactions are also known to be constrained by causality constraints. So the amazing thing in gravity is that just as a basic kinematic level, before going the math, you expect that S is equal to R plus small. Causality, just at the kinematic level of enumerating the spin of interactions, you deduce that the correction to Einstein gravity cannot be large. That's very special about gravity. But I'm going to go to that at the end of my talk. That's all because of this kinematic effect that whenever you write interactions with graviton have spin, and whenever you write interactions between them, you get these polynomials and spinners in front of you. Okay, this effect makes gravity so much more constraining than other forces. Okay? So this is all words. Let me tell you the actual tools we use. And still has is hand raised, but I believe that's like a remnant.
No, I put I put it back up. It doesn't
Okay.
matter how the indices are contracted here.
Oh yeah, it does matter which channel you have, but there's always going to be some. Yeah, it does matter. Yeah. Actually, if you put the Ricci scalar, then that's like 0 by equation of motion. It's removable. These are you should think of these as polynomial in the Riemann tensor, and then there are different index contractions. The way to list these index contractions is for each helicity. Well, the sensible way to enumerate that, modulo integration by part and everything, is for each helicity, you write down the minimal. For each helicity choice, you write down the minimal power of spinner, minimal polynomials and spinners you can write down, and then you multiply it by polynomials in S and T, and that will enumerate all of the contact interactions you can have in gravity. Yeah. And this paper here has very helpful way to do this. List these minimal spinners, and even in a massive case, they give you an algorithm to generate what they call the ring of contact terms. Okay? So yeah, that's the sensible way to enumerate those. You can also enumerate index contraction, and the dictionary between these was spelled out in that paper. Thanks for the question. Is another question?
Yeah, is there an r² phi term? Why is that not allowed?
R² phi. Riemann square phi. Yeah, it should be somewhere. Yes.
I'm interested because the 3-point couplings like correct the subleading soft theorems, and like that's one that involves this.
Yeah. Well, I guess it should be here. Yeah. It should be here. But yeah, it has spin too. There's no. It is probed by dispersion relation. There's no. You can probe it in the. Yeah, it's a true. Yeah, you can probe it in the scalar graviton scattering. Yeah. Yeah. Thanks. Okay. So let me move on and say how we actually proceed. So well, actually, I have one more formalism slide. So we studied causality constraint on to-do scattering, and I'll just make 2 qualitative comments. You might, what does causality mean? You might say that it means that you don't get time advance in scattering, and at fixed angle scattering, this is very subtle, and actually there's a nice argument in this paper that actually you can get time advance, but basically you cannot prove that there cannot be a time delay, and the reason is that what do you mean by saying that there's no time advance at fixed angle scattering? Is that what you do is you take your incoming particles, and then you imagine that they hit at a point, and then you draw the future-like cone of that point, and you ask whether you arrive at infinity faster or than that. But this is not how scattering works. There's not an interaction point in the quantum theory. It's just not how it works. So there's really like some all we know is that things come in and things come out. And so there's no precise way to compare the arrival time at fixed angle. And if you scatter like objects that are extended objects, that was basically the example, then you're not surprised if like billiard balls, you're not surprised if it comes out earlier than the velocity it's moving. If we have repulsive forces in general. Okay. So the region where causality is actually constraining is the forward region. And the reason is that the forward region, so if you create this particle here at point 1, you insert some like shake the field here, there's a chance that in the forward direction, there's a chance that you spill out of the future-like cone of that point where you initiated the particle. So causality is partially constraining in the forward region, and this is why this rigid limit and the spin that I described before, that's why the rigid limit is so important in this business. Okay, it's just because causality matters mostly in the forward region. And the other thing I want to say is that you might think that causality has to do with the particle not being able to move faster than light from 1 to 3. That's not correct. Particle can actually move. Particle can actually be visible here because you can have correlations between a point here. And here I'm thinking about like asymptotic measurements, for example, of the gravity field or electromagnetic field. It's possible to have correlations between these measurements that are space-like. We always have that in quantum theory. causality means that the amplitude to go from 1 to 3 cancels with the amplitude for antiparticle going from 3 to 1 when you compute a commutator. Right? It's really about space-like commutators. So crossing symmetry, causality really, the strongest statement is crossing symmetry. Relates those two amplitudes. Okay, so yeah, that's the other basic thing. So there are a lot of technical issues in making this statement precise, but the physical picture I think should be clear. The issues have to do with there are issues in proving crossing symmetry that have to do with the fact that this LSZ formula is done at fixed angle kinematics, which don't overlap with this blue screen. But apart from this technical issue, this is the physical picture which I'm going to have in mind for the rest of the talk. Okay. So this being said, what are our axioms? So the two things we use is our analyticity and boundedness. So analyticity, so this causality argument gives you analyticity in the energy plane, which basically means that you have a crossing path from positive S, from the S channel to the U channel. So what we assume is that there exists a crossing path in a region, this crossing path specifically that we're going to use, and we're going to assume analyticity outside this path. This crossing path goes from the EFT cutoff on the S channel to the EFT cutoff on the U channel. And we assume that this path exists for physical with momentum transfer that are below the cutoff. So we do energy experiments with momentum transfer less than the cutoff, and we assume that this path exists. That's a physical point and a physical point. And yeah, and we need enough analyticity basically to be able to push this contour outside and say that this is an integral at infinity that vanishes. And for that, we need the boundedness property. And this limit here is the rigid limit, large S at fixed t. So we need to be able to bound what happens there. There's a naive statement that is often used in this business that I would quote. The naive statement that, well, it's not so naive, but it's kind of natural. Maybe I could say the momentum space statement is that M grows less fast than S squared. So M over S squared vanished infinity. And that means that twice subtracted dispersion relation converge, or spin 2 some rules converge. An example is string theory. So at tree level, you have S squared plus alpha prime t. So in the physical region where t is negative, it grows slower than S squared. Okay, and then you can discuss whether it's true or not. I'm not going to go there. And okay, so in the axiomatic quantum field theory, it's known as the Frosser bound. But actually, it would, yeah. But the hard part of the proof of the Frosser bound is to bound Fourier transforms. And actually, I will not go through any of those, because the assumptions that we're actually going to need in this talk to constrain EFTs are much weaker. We're only going to need that smeared amplitudes divided by S are bounded at high energies. And smear amplitude means that we integrate against wave packets that have compact support in momentum, because we're just going to do low energy experiments with momentum less than the cutoff. And we can assume that such wave packets have like fast enough power law decay at large impact parameter. And basically that makes it trivial to estimate Fourier transforms from impact to momentum. So this minimal assumption is very easy to prove and justify. And basically it means that we can use dispersion relation with spin higher than 1. This is what we actually use in this work. And I should mention that you can ask, do all these causality things, do they work in quantum gravity, blah, blah, blah. It's not axiomatic field theory. I would just add that in the context of ADS CFT, we can, all the sum rules we described today, we can embed them and give you CFT sum rules that are valid at finite curvature radius, that up to small curvature correction. So they're rigorously valid in ADS CFT. So I think there's at least one example of a theory of quantum gravity where this axiom is the right one. Yeah. But I would not stress that. So let me tell me how we use that. Let me tell you how we use that. Okay. So we have these dispersive sum rules. By this time, we've seen this contour a few times. So we use that. If we deform the contour to infinity, we get 0. This is twice subtracted 1. And we're going to make it symmetric to an S and U channel just because it simplifies life. Because crossing symmetry is so important. So 0 is equal to this contour integral at infinity. And that gives you a relation between EFT observables and UV physics. And we choose a contour such that the UV physics enters through the imaginary part. And the important point is that the imaginary part of the amplitude has a partial wave expansion, where the imaginary part of the, so it's a sum of Legendre polynomials, but each of the coefficients is positive. Note that we're going to be working in a physical region where t is less than 0. The Legendre polynomials are oscillatory. I'm not saying that the imaginary part of the amplitude is positive. It's not. It is just a positive sum of Legendre polynomials. That's all we know. And we're going to be able to make mileage from that. It's not positive, just a positive sum of Legendres. Is that? So we get effective figure observable from this contour integral that are equal to this. And if you apply this integral to a 3-level EFT, as parameterized before, you get some kind of series in EFT coefficients. So that's gravity, that's like 3-level gravity, graviton exchange. And then you have all these interactions. And basically we've integrated out S, so we're just left with functions of t. And here we have a sum. This average sign here is a sum, it's a positive sum over these AV states. So you can think of this as a positive measure. The only thing that's going to matter for this talk is that this measure is positive. It's actually bounded, but we'll not use it today. So we can write infinite series of EFT couplings as averages over UV physics, sums over unknown UV physics. And we're not going to say anything about this UV physics except for the fact that its partial waves are positive by unitarity. That's all we know. So if we didn't have gravity, there's a simple way to use this sort of sum rule is you put t equals 0, and then you isolate. So if you don't have gravity, you drop this term. T equals 0, you kill everything else. So that gives you a sum rule for G2. And if you put t equals 0, the Legendre polynomial just become 1. So it gives you a very simple sum rule that G2 is a sum over all the states of inverse power of their mass. And that's clearly positive. It's a positive sum. And this was observed, and this was the key to this. This was the inequality I started this talk with. Later today, not right now, but later today, we'll keep gravity not equal to 0. Then there are some interesting things you can still say. So this sum rule you should think of as convergent when t is negative. So this thing on the left is positive. And if you think about those sums, it's easy to prove that the only way that such a sum can diverge as t goes to 0 is can only diverge with a positive coefficient. That's the only way that the positive sum of Legendres can diverge. So it's really immediate from these sum rules that gravity is attractive. So great. That's the most important feature about gravity is built into this. But once you have gravity, there's a challenge that you can see, because how do you bound other couplings? So we see that this term is positive, but it comes from a divergent limit. T goes to 0 is divergent. If you try to take a Lorentz series on both sides, it doesn't make any sense because you start to manipulate divergent sums. And as all of you are familiar with, you can't predict the sign of a divergent sum. You can write -12 as a manifestly positive sum, 1 + 2 + 3 + 4, and so on. And like the fact that it's positive doesn't tell you anything about the final sign because it's divergent. So in this business, you have to be extremely careful to only manipulate sums that are positive and convergent. And we'll tell you how to do that at the end. But I want to tell you more about the non-gravitational case first, because it builds a lot of intuition. So without gravity, the trick is to expand around forward limit, which is, t equals 0 is what zero momentum transfer is forward. So if you expand this sum rule, you get Taylor series like that. But remember, you can have many, many different sum rules. So you can have more subtracted one. And the next one gives you probe things that grow like energy 4. So G4 is like the quotient of 4 powers of Manastam. So you can probe it with the spin 4 sum rule. When the spin 4 sum rule kills those two things, which are spin 2 interaction. Remember this idea of that interactions have spin. So we have these sum rules, and then you just expand both sides in power of t. The first thing you get at t equals 0 is this sum rule we mentioned. If you look at the quotient linear in t, you have to take a derivative of a Legendre polynomial, so you get something that goes like the spin Casimir, and you get this sum rule. And there's something cool that happens for the next guy. So okay, you can easily get a sum rule for G4 by setting t equals 0 in the second one, but you can actually get two sum rules for G4. That's something that strikes you when you start enumerating that. And physically, that's because of crossing symmetry in the IR. It's because the quotient of S4 and the quotient of S squared T square are related by crossing symmetry. It's only one symmetrical polynomial you have. So if you compare those, you get a sum rule that has to give you 0. It will play an important role in a second. But let's look at this sum rule. So this is for the sum rule for the quotient of STU. Obviously, from this sum rule, you get an upper bound on G3, quotient of STU interaction, because it's 3 over M6 minus something. So that's negative, forget. And the upper bound is a 3. And the point is that this average, we're probing effective EFT coupling is a scale M. The average is only over UV physics above M. So M is 1 over M squared. 1 over M6 is less than 1 over M squared times a constant. So we get this upper bound is trivial to prove. The thing that's harder to prove, and that was not done until like last year, as far as I know, is to get the lower bound. The issue is that you have to bound the spin of what you can exchange. And if you have a strongly interacted UV physics that you don't know anything about, you don't know what the spin of what you exchange. So you can write G3 as 3 over M6 minus, remember that a useful way to think about angular momentum is that it's like the impact parameter of the states you're probing. Yeah, they're related. So this J6 over this J square over M6 is like impact parameter square over M4. So to probe a lower bound, you effectively have to bound the impact parameter at which new physics can be visible. And it's not surprising that you have a 1 over M4 at fixed impact parameter, because we explained before that STU grows in a rigid limit like a spin 2 interaction. So that's why you have M4. So the spin of an interaction predicts the power of M at fixed P. So we need to bound the impact parameters of intermediate states. And the key is this crossing equation. If you stare at this equation a bit, you realize that it prevents J from being big. It's balancing J square against J4. So this is basically the secret sauce. So yeah, we have to use these null constraints. So this was done, was used last fall. And the fact that this UV average gives 0, it looks weird to have a constraint on the UV, but it's not really a constraint on IR physics or on UV physics. It's a constraint on the way that UV physics can couple to like states, because we're scattering like states. And if you manipulate this constraint using Cauchy-Schwarz, you prove the following thing. You prove that crossing symmetry means that the average impact parameter that contributes to these sum rules is less than the cutoff. So every state above the cutoff M, you can pretend that they all have size less than 1 over M. Does that's a surprise. And because many years people have been saying in gravity, or you have black holes, the size of a black hole grows with energy, right? Also strings, the size of a string, the length of a string grows with energy. Crossing symmetry means that black holes cannot couple strongly enough. States which grow with energy cannot couple strongly enough to matter. These sum rules are all dominated by, basically, it's basically because of this power. These sum rules are dominated by states just at the cutoff, and which are not bigger than 1 over the cutoff. So that's a very key thing, and it's a consequence of crossing symmetry. We can bound the size of the coupling of things of large size. It's negligible. That's a key lesson. And once you understand it, once you've internalized this lesson, well, you get two-sided bounds on everything, right? So once you've bound this term, similarly you bound everything else. So you get two-sided bounds on all EFT coefficients, starting from in terms of the first one. So you get the lower bound, upper bound. So this is a tree that we discussed analytically. This bound. And some cool thing about these numbers that they don't grow. So effectively, qualitatively, in effective theory, coefficients cannot grow differently than the geometric series. Can have different patterns, but they cannot grow faster than geometric series, as you would expect from integrating out a heavy particle. So we justify effective field theory counting from causality, power counting. So this is the main result of this talk, and I think in 2-3 minutes I would tell you what. Try to wrap up. Maybe I need five minutes.
Yeah, that's fine. Sure.
So in the non-gravitational case, can tell you a bit more. So you can make exclusion plots, and you can systematically add more and more of these crossing equations and get better and better constraints, but actually converge quite fast, and you get these sort of constraints. Yutin later today, I believe, will tell you there's some very nice way to analytically understand these constraints from the forward limit. So yeah, this slide probably doesn't make sense yet, but it would connect with this talk. The other thing that I can mention is that when you make this exclusion plot, so this is for this S4 interaction versus the STU interaction in units of the leading one, you get interesting exclusion region, and they have some kinks. And actually, you can show that these exclusion regions are optimal because we can realize theories of the kinks. And okay, forget this thing that's written here. Yeah, so there's this thing here is just if you exchange a heavy particle of spin 0, you just get this kink. The kink to the left is a bit weird. Is this theory? It's not a theory. Like I'm not seriously saying that this is a sensible theory, but if you compute the partial wave expansion of this thing, you find that the imaginary part only is a sum of Lejeune polynomials with positive coefficients. So it's something that is not ruled out by the current axioms of S-matrix theory. So until it's a challenge for the audience. If you can tell me how to exclude this, if you can tell me what's wrong with this stupid theory, which looks obviously wrong, if you can tell me exactly what's wrong with it and how to rule it out, then we could get better exclusion plots. But yeah, that's all I have to say about this scalar case. And I want to say, okay, skip this. I want to say briefly, what do we do in the case of when we have gravity? The trick is to go the forward limit diverge. So in short, the trick is to go as far away as possible from the forward limit as we can. And the trick is to use these, but yeah, we have to go away from the forward limit. I'll say it very quickly. It's not going to make, hopefully it will make it, the idea will make a bit of sense. When you go away from the forward limits, you run into a problem that you probe infinitely many couplings. But I told you that there are multiple ways to measure these couplings, so you can eliminate them. Everything which grows faster than spin 2, you can eliminate. And you can write down this improve sum rule, which for any transverse momentum in a finite range probes exactly 3 couplings. in terms of some average of every state. And then the trick is to combine these sum rules in a clever way to get the positive average on the right. And we do this by constructing wave packets that are spread out between momentum from 0 to m. And if we construct clever wave packets such that each state on the right contributes with positive sign, then you've proved an inequality that's satisfied by a linear combination of these three things that appear on the left. So that's the recipe. We go away from the forward limit using crossing symmetry. And you can make an algorithm that does that for you. This wave function that you need, they're kind of crazy. They have two properties. They need to have compact support and momentum, and they need to be positive in impact parameter. And such things exist. that's interesting, but they exist. And I don't know a good way to make them. In practice, we just make some giant polynomial ansatz and ask the computer to find combinations of positive at each impact parameter. So, and the computer finds those, and and there's some example bounds we get. So this is for scalar coupled with gravity. And one thing we learned, for example, from these bounds is that the quantity which was so much stressed to be positive before, G2, this bound for different dimension, our right-side axis is G2, quotient of S square, this quotient of STU. Now some slight negative allowed region is allowed, it can actually be negative. And can interpret this in a simple way. It was anticipated by some people. Basically, it's because gravity is attractive. It gives you a time delay in any scattering experiment. So you can tolerate that other interactions give you a little bit of time advance and still come out even. So this tip here is when you somehow break even and don't have any time advance or delay in certain scattering experiment. So, but yeah, gravity shifts things a bit to the left. And now we can tell you exactly the number, how much it can shift left by its Planck suppressed effect. And yeah, using this technology of wave packets, in the case that we don't have gravity, we produce exactly the exclusion plots that I showed you before. So it's all consistent, but it still gives you something new because, well, it gives you bounds that smoothly, that don't even change when you add gravity. And also these bounds that use wave packets are much easier to justify because instead of using the Frossard bound that m over s square vanish, you just have to use this much easier property that m over s is bounded in after smearing. So I'm essentially finished. I wanted to say what we expect in graviton scattering. I will just quote result without explaining what it is. In the case of supergravity in 10D, we prove the following bound. So there's a famous term that's an R4 interaction. So you have gravity plus R4. And it's kind of a super convergent case. So you have the amplitude, you have unsubtracted the Poisson relation would converge. So we can prove a nice upper bound. So we managed to prove this upper bound that suspiciously close to 3 and units of the first particle of the cutoff. So one thing that's interesting about gravity is that if you shut down Newton's constant, everything else is to shut down. You can't essentially, well, in the case of supergravity, this formula says that you cannot have like R4 gravity without having R. Cannot. And there's a precise bound, the relation between the coefficient in terms of the mass of the first heavy state that you hit. This R bound is satisfied in string theory, of course, which give a number like 2.4, less than 3. We don't know a theory that saturates it. It's also possible to get a lower bound because in gravity, right, you can write Newton's constant as a sum over heavy states. Gravity comes from the UV. It's very unique in that way. But if you write Newton's constant as a sum over every states, that means that the UV spectral density cannot be 0. So you cannot have gravity without having other effects, which are Planck suppressed. And these people showed that you get a lower bound in 10D supergravity, that you get a lower bound. And amazingly, they got lucky. Their lower bound seems to be saturated somewhere on the moduli space of type 2b, which really suggests that there's at least one string theory that we can solve with bootstrap. That's a very important discovery. Yeah, so I'm done. Should also mention, like, it's very interesting to compare these sort of constraints with the space of allowed theories. It looks like right now the constraints are way too conservative, and the theories that we actually know make sense live in a smaller subset, small subspace. So it's really exciting. Are we missing something? So I'm finished. So thank you all for your attention. So I discuss the main message of this talk is that causality gives you two-sided bound on generic EFT coefficients. So we set out studying the space of effective theories that are causal, and now this phrase, I don't know how to think about this, but it's kind of redundant. You could be studying causal whatever, and you'll discover it has to look like an EFT. So we're studying the space of causal S matrices, whatever that is. And yeah, causal, yeah. And so yeah, this is going to lead to rigorous bounds on all possible causal modifications to GR. That is work in progress. There's a lot more to explore. We use the fact the imaginary part is positive. It's also bounded. That's going to be useful. Hopefully the space of allowed theories is going to contain interesting things. We should try to find theories that realize these kinks that saturate these bounds. Should find a way to probe dimension 6 operators, things that have spin 1 that are listed at the beginning of this talk. Like a lot of standard model, interesting things, the standard model grown in like spin 1. We have not said anything about those yet, because they're killed by 2 subtracted dispersion relations, loop effects. Another question is that I briefly alluded to the fact that we have a machine that any of these flat space, some rules that we can prove, you can uplift it and get a rigorous constraint on the CFT or gravity in ADS, which is great, which means that ADS space is at least as constraining as flat space. It would be nice if it's more constraining. We don't know. So yeah, we've been studying, physics has been studying causality for over 100 years, and we're still learning stuff. I think there's much more surprise to expect there. So thank you.
Okay, thank you very much for his nice talk. So we have time for questions. Andy?
Could you say a few words about the relationship between causality and crossing? Are you equating them?
No, I mean, crossing is, I would say that crossing is the strongest implication of causality. You could also take like let's put it like this. You can do
Causality
classical,
implies crossing, you're saying?
Yeah. That's the arrow. Yeah. And you can do like classical experiments where you have a wave packet that's very localized on positive energies. In this case, causality is really a statement that the particle cannot come out faster than light. But this is not the strongest statement.
That's not very well defined. So in gravity, what?
I'm using the asymptotic structure. I'm studying asymptotic gravity in asymptotically flat spacetime, and I'm anchoring everything to the causal structure at infinity.
Well, I don't know what exactly you mean by that, but what would you say about something like, for example, things like Min-Wallace things where you have unitarity but not crossing? His 2 + 1. There's an S matrix which is unitary but not.
Yeah, it's a classical limit of this constraint. So let's put it like this. So we crossing. Sorry, causality gives you analysis in the upper half energy plane. A subset of that is that if the classical limit, you're probing just a little neighborhood of some positive energy. Meanwhile, and all are using like a region that's like that. Okay, and that's like the classical causality constraints probe like this region of the complex plane. But the full
Oh,
power.
I'm talking
record-
about their
yeah.
2+1 S matrix where they solved they constructed a unitary S matrix for 2+1 model, and it
Oh, in 2
wasn't.
plus 1D, in 2 plus 1D. Oh,
Yeah.
okay. No, this is okay. Yeah, this was in Simons theory that are not.
Insurance Simon theory,
Yeah. There you have some long range topological order, and that seems to be the explanation. That's the explanation they propose for why crossing symmetry does not work in the simple way.
Yeah.
Because of this, there's some phases that connect things, but this needs to be understood better.
Well, so the reason we like causality is we think, the grandfather paradox, that classically, if we don't have causality, the present can't predict the future and we can't have consistent laws of physics. But if we construct a unitary S matrix, what further constraint should there be?
No, I think in 2+1, the way we think about it is that there is still some crossing relation. It's just that there's some correction to it. That's a picture that they propose also. There's some correction to it because of some phases, but you should still expect that this, when formulated properly, there's still a causality constraints that are related to analyticity of the S matrix, even in 2+1D. It's just a matter of figure. It's not. It's not. I'm speculating that this will be understood, but we don't know exactly what the constraint is, but they suggested that there would be one.
Okay, so in quantum gravity, you want to say that I mean, the light cones aren't well defined, right? So what?
I'm using a symptotic light cone from starting from a place which is very flat, far away. I'm assuming, and the main assumption is that the main concept you should think about, which the minimal concept I will need. I'm not saying I have it. The minimal concept I will need is some notion of being able to measure, say, the gravity field at some time on scry minus, and say that what's the image of that on scry plus.
Yeah, I don't know how you do that. I don't know how to canonically, even in classical GR, to associate a cut on scry minus with one on scry plus.
So the way I'm thinking about it here is we do it canonically at very large impact parameter. I think we agree that it can be done.
I'm not sure I agree with that.
But if we're starting from flat space, in flat space we agree we can do it. If there's no energy in the space time, we must agree that we can do it.
But the moment you have, but the moment you have any excitations, you start inducing super translations and the light cones get shifted around.
Yeah, but if the excitation is put very far away, there's no pre-existing something in the body. We can discuss more later. I think that's an interesting point. Maybe we can look at other questions. I agree, but yeah, I'm assuming implicitly, if you want to know what we're assuming that we're assuming that there's some map between, in the forward direction, scry minus and scry plus. Away from the forward direction, I have no idea. I'm talking about forward scattering between scry minus and scry plus. We're assuming that. At fixed angle, I don't think there exists such a map. We're not assuming that at all. It's only in the point that's forward.
Mm.
Yeah.
Okay, maybe we discuss this further in the panel discussion. But there's another question by you, Tim.
Hey, Simone. Hi. Yeah, I just wanted to ask you a little bit more about the STU amplitude. And did you guys look at do the STU and the scalar also spans the other coupling space? So in the 2D plot, it spans most of the region. And is it like is this a consistent phenomenon whenever we look at other coupling regions?
Changing slides. Yeah, this one. Yeah, this STU amplitude.
Yeah.
Well, Well, like one thing I can say is just mathematically, it's a kink. So if you think about the higher dimensional region, it's a point. This theory is a point. You can ask how fat the region is around that point. As you know, right? I mean, we haven't systematically explored, but when you start making 3D plots, you find that these things usually are very narrow and couplings are highly correlated with each other. So yeah, in some sense, I believe that like if you're close to the, if you make one measurement of G3 and you find that you're like here, then presumably you predict everything else with some small window.
So yeah, okay, yeah, and so one would imagine that indeed these kind of linear combinations of STU and spin zero, they will also span any higher dimension space because they're also correlated.
Yes.
Yeah. So I guess then.
You're wondering whether they to the extent to which they span the multiple.
Yeah, exactly.
Yes.
Yeah.
This I don't know.
Because probably the comment I wanted to make is because the linear, if they actually span most of the space in the higher dimension, then it sounds like, because you know that STU and the spin zero, they automatically have this kind of large spin suppression. Mm-hmm. So does it mean that like actually the geometry itself is already implied, because if these things span the entire space, most of the space, that means that most of the space actually satisfy these higher spin suppression. That it's not something that you need to put in, but it's actually implied already.
Yeah, this is also what I generally expect. At least it's just my as a physical matter. I think that large spin suppression is that statement, right? It's just we have bounds on how large spins can contribute, and I would be surprised if we need to add manually other things. But it's interesting that right now it seems to be this phenomenon of large suppression for a non-expert is this phenomenon that seems to be more suppression than expected from what we could prove. But I think just a basic fact. This plot was made using only some rules, and I think we need to add more and systematically explore the constraints before we conclude that we're really missing something.
Yeah, I agree. Thank you.
Okay, so Andy, do you still have another question, or?
No, I'm sorry.
Oh, no problem. So I remember, I think, Simon, you will be around at least for a fraction of the discussion session in about 3 hours.
Yeah.
Okay, then maybe I suggest that we postpone any more questions to Simon and to the panel discussion, which starts at 6 p.m. European time. And now we have a break, and we resume in about 10 minutes with Ashok Sen's talk. No, in about 20 minutes. It's 3:30.
Thank you.
Yeah, thanks.